Hi and welcome to this video. This video has something to do about the law of conservation of momentum. So far, there has been different systems that we practice the law of conservation. One of them is law of conservation of mass, which means that mass cannot be created nor destroyed. Same thing with law of conservation of energy, where energy cannot be created nor destroyed. Or from the most previous topic that we went over, energy from one point compared to another energy, it will be the same, the total energy. However, it's the form of energy that is being changed or transformed from one form to another. For example, from spring energy to potential energy and to kinetic energy. So at this point, we will learn the concept of law of conservation of momentum. Okay, so law of conservation of momentum. So it means that momentum cannot be created nor destroyed. Okay, and this concept of law of conservation of momentum has something to do with what we call collision. Collision, or when two objects collide. Okay, collide, it's either collision happened accidentally or collision was made in purpose. Okay, so it was made in purpose. So it means that in order to experience collision, there should be two objects that are moving and that the condition that they should collide. So in our case, let's start by having, let's say this is a leveled or even surface where we have object number 1, and then let's call this one object number 2. Object number 1 and object number 2 might have two different masses. So we don't have the same mass, and they might not be traveling at the same speed. So if objects don't have the same mass and they don't have the same speed, they don't have the same velocity, then definitely you don't have the same momentum. Okay, they don't have the same momentum. So it means that when these two are moving and there's a possibility that they will collide. For example, if the second object is not moving and object number 1 is moving towards the right, then that's a possibility that collision will happen. And let's call this condition as the initial condition. So let's call this initial. Initial being represented by the letter I. And since there's no collision yet, so let's call this one before collision. Okay, so before collision happened. So before collision. And law of conservation of momentum is all about collision. So when collision happened, there is supposed to be a law of conservation of momentum, or law of conservation of momentum is being applied. Okay, the concept of law of conservation of momentum is applied. So possibility 1 and 2 are moving. 2 is moving slower to the right. 1 is moving faster to the right. Then it will catch up and hit them. Okay, it will hit object number 2. So at this point, we have object 1 and then we have object 2 experiencing what we call collision. So this is object number 1 and this is object number 2. And if we call this one the initial before collision, let's call this one the actual collision. So actual collision happened. Actual collision happened. Last but not least, as soon as they bump into each other, you have different probabilities. Okay, you have multiple probabilities. For example, I have these two circular objects here. I have these two circular objects. Okay, I have two circular objects that might be identical in terms of size. So please pay attention as I'm going to explain different probabilities. Probability number 1, when they collide, as soon as they hit each other, the first probability is that both of them will bounce off, so they will move away from each other. Hit, and then they bounce off. Second probability, when they collide or when they hit each other, it will stop from moving. Another probability is one of the object, okay, one of the object will stay. For example, see, this object will stay, then the other object will move backwards. Or the opposite. As soon as they collide, the object on the left side will stay, will not move, and the object on the right side will move to the opposite direction. Or they might get entangled together and now they're moving to the right together. Or backwards. So different probability. Okay. Once they hit each other, now it's going to be moving. The other one's moving faster than the other, so they're following same direction or the opposite direction. So different probability. But for sure, that probability can be answered using the concept of law of conservation of momentum. So as I'm going to continue drawing this, the object will be the same. Okay. In this law of conservation of momentum, let us all make the assumption that matter will not be destroyed also. Okay? Matter will not be destroyed, meaning that the mass of the object will be the same. It will not become smaller. Okay? It will not increase. Okay? You will not break it into smaller pieces, but instead, it will retain its old form. So this is our condition we call final. Okay? So final, F, or this is what we call after collision. So let me just write it here in the bottom. So after collision happened. Now in this condition, okay, we all know this is matter. There's motion, as momentum is defined as the motion of matter. Okay, mass in motion. Okay, so instead of using subscript, because sometimes subscript will cause us some confusion, why don't we come up with a rule? Okay, why can't we come up with a rule? Let's use this rule, and I will write the rule right here. Okay, so I will write the rule over here. Use the rule. Okay, what rule shall we use? Let me just move it down so you can see. So rule that you will use. Uppercase, okay. Use uppercase for the first object, for object number 1. Object number 1. Which means if we're going to figure out mass will be uppercase M, and then the velocity is uppercase V. Now for the second one, okay, uppercase is for the object, for object number 1. So our rule is that lowercase, let's use lowercase for object number 2. So instead of using subscript M sub 1 and V sub 1, let's use uppercase and lowercase instead. So object number 2. And this will give us M lowercase and lowercase b. So as I mentioned, so why don't we just write it here? So mass of the first object is M. The velocity of the first object is uppercase V. The lowercase m for the second object, and lowercase v is for your object number 2. For object number 1, still the same. We use m and then v. And m lowercase and then lowercase v for your velocity. Now, as we have learned in the past, velocity means speed and direction. So if there's a change in direction, definitely your velocity in the beginning is different from the velocity in the end. Or if it's 5 meters per second, now it's 3 meters per second, then you have a different velocity. You also have a different velocity if it's 5 meters per second to the right and 5 meters per second to the left. It means that the direction changed. Now, if I am going to write the definition of momentum, which means P, which represents momentum, is mass times the velocity. And velocity, you need to consider that this is a vector quantity, so therefore we have our distinguishing vector arrow on top of velocity to denote that this is a vector quantity. Now, how do we figure out the total? Okay, so every time there is a collision, you're not talking about the momentum of one object. You're not talking about the momentum of another one object. You're not talking about object 1 or object 2, but we are talking about the momentum of both object 1 and 2. So your system basically is the collision system, or both of them. So you cannot separate one from the other. Before and after, or during collision, you will have to consider both object 1 and object 2. Okay, object 1 and object 2. So from our previous lesson, momentum of object number 1, and then let's use the equation for momentum to solve for the momentum of object number 2. Now, if we analyze this, the velocity changed because there is a change in direction, there is a change in the magnitude, means 5 meters per second to 3 meters per second, or 3 meters per second to 5 meters per second. Then we can consider that this, in order to denote which one is before collision, let's put this one right here, which is the initial velocity. The same way over here, initial velocity. So now that's the only subscript that we will use in order for us not to get confused on what happened. So this is before collision, and then this is the initial momentum of the object, okay, the initial momentum of the object, object 1. Then we can say that since it is object 1, all we have to do is use the same equation, which is mass times velocity. So the mass of object number 1 is m, and then the velocity before collision, or the initial state, is v sub I. So that will be our momentum for object number 1. For object number 2, then we will use the designated mass, which is the lowercase mass m, and lowercase v sub I. So that's the initial condition. So if we will add those two numbers together, this will give us the total momentum before, okay, so before collision, which is the sum of those two, and that is m v sub I plus m v sub I. So this will be your initial momentum, the sum of those two momentums that we have. Now, just like what we did on the first one, initial, okay, so initial momentum. By the way, the actual collision, we always study before and after. The actual collision happens, there is a gap between them. So that will be your equal sign. So final F, so it means that this one is your final velocity. It's either it's moving to the left now, or it's slowed down, or it's stopped moving, and this one is also your final condition. So now let's talk about the final condition. Let me use a different color so it will designate our final condition. So the momentum for object number 1, the momentum for object number 2 is simply the product of mass and the velocity, but since this is the final condition, so your uppercase V should be provided with a subscript of F, which means final. Though I'm using subscript, this subscript is basically just subscript to show that it's the final condition, and then mass multiplied by the final velocity. Then if you take the sum of those two, this is the total momentum after collision. So this is after they have collided, okay? After they have collided. So this is mass of V sub F plus m V sub F. The condition according to the law of conservation of momentum is that those two numbers should be equal. So they should be the same. They should be the same. So the momentum before should be equal to the momentum after. Momentum after. But if you notice, I have left a space over here because I want to emphasize that we're not talking about, oh, this momentum should be equivalent to this momentum. They will not be equal. Okay? This momentum will not be equal to the momentum here. Instead, law of conservation always states that it is the total momentum, which is before and after, as it states in the definition of two colliding objects. Two colliding objects which represents the system. So two colliding object means total momentum. So therefore, let me just correct this and add the word total momentum before and total momentum after. So we can actually finalize our statement where it says mass and the initial velocity of object number 1, or the product of the velocity and mass of object number 2 before collision, you add those two numbers together, is simply equivalent to the mass of the first object multiplied by the final velocity of the first object, and of course the product of the velocity and mass of the second object after collision. So this is basically the law of conservation of momentum represented in mathematical form. And in case you are being asked to derive the equation, this is a simple derivation of the law of conservation of momentum. In the next part of the video, I will be showing you an example on how law of conservation of momentum exists.